Hello everyone. Today we are going to discuss together one part related to MOSFETs. So last class we discussed one of the circuit applications of MOSFET. Today we are going to continue discussing one configuration for MOSFET, which is constant current biasing. And then we will discuss some applications of MOSFET. So the objectives of today's class is to investigate the current biasing of MOSFET device, what the meaning of current biasing, and discuss the different applications of MOSFET like switches, logic gates, and amplifiers. So starting firstly with the first thing, which is constant current biasing. So what the meaning of constant current biasing? We have some applications, guys, we need to have like constant current in a certain MOSFET. So in order to do that, we need to investigate together the following circuit. So as you can see here, we have this current, which can be considered as reference current, and we have three MOSFETs. This MOSFET M3, M2, and M1, and we would like to have a similar current here in this MOSFET. So this circuit actually is going to control the current in this branch to be similar to that branch. So how can we do that? In order to understand that, let's investigate the circuit we have here. So this is already an example in our textbook, example number 314. So the numbers are, we have I reference equals 0.2 milliampere. So in this example 314, we have I reference 1, because this is going to flow in this branch here, equals 0.2 milliamp. And in this example, we assume that V plus equals 2.5 volt and V minus is minus 2.5 volt. And we assume that the threshold is constant for all transistors, 0.4 volt, and Kn for transistor 1, this one, equals Kn1 equals 0.25 milliampere per V square. And the lower two transistors, we are going to assume that the lower two transistors are identical in everything. And we will see how this is going to achieve the same current in the branch here. So let's say now for transistor M2 and M3, we have Kn2 equals Kn3 equals, as given in the example, 0.15 milliampere per V square. So these are the parameters we have. So now we just need to investigate what would be the current in this branch. We need to get that current and calculating VDS1 in order to figure out what would be the mode of operation of this MOSFET. Firstly, for this MOSFET guy we discussed in the previous class, all of time this MOSFET is going to work in saturation mode. So since we can start from MOSFET now number 3, so let's say here for MOSFET M3, we know that for M3 now the current is given. So I drain is well known, which is I ref now. So I reference equals I drain, which is 0.2 ampere. So we can say now I D3 equals 0.2 milliampere, which can be considered from the relation of saturation of this MOSFET equals Kn3 times VGS3 minus VTN whole square. So this is the relation again in case of saturation mode, and we know all of time in case of load transistor where gate and drain are short circuit together, so this would be all of time as saturation mode. So let's see, guys, now. In this case, let's substitute in the relation here and getting our values. So we have, from this relation, we can say VGS equals square root ID3 divides K and 3 plus V threshold. Just getting the square root for each side. So you will get V gate to source equals square root IDS over Kn plus VTN. Now let's substitute in this relation. We have current equals 0.2 milliamps. So 0.2 divide Kn for transistor 3, which is 0.15. So this is divide 0.15 all plus VTN, which is given here 0.4. Substituting with the values here, you will find VGS3 equals 1.555 volt. So this is now the value of V gate to source for M3. As you can see from this circuit, you have transistor M2 and M3. As you can see, VGS2 and VGS3 are equal. So we can say now for MOSFET M2, we can say VGS2 equals VGS3, which is 1.555 volt. Since we have VG for MOSFET S2, and we need to investigate what would be the current, so let's make a relation now for MOSFET M2. So we can say now ID2, which is unknown, this is the required current. We can say ID2 and also assume it's working in saturation mode. So ID2 equals Kn2 times V drain to source 2 minus V threshold 2, all square. So we have Kn, so we can say Kn now equal 0.25, sorry, for 2 equals 0.15, so this is 0.15 times V drain to source, which is V gate to source, not drain source, gate to source. So V gate to source, which is 1.555 minus threshold volt, which is 0.4, all square. So we will find, if you substitute here, you will find that the current is the same, 0.2 milliampere. So this means, guys, if you select the lower two switches or the lower two MOSFETs with the same or identical MOSFETs that having the same Kn, and as you can see, gate to source are equal because they are connected in parallel like that. So in this case, we are sure that the current which is going to flow now in this drain would be the same as the reference current here. So this is the basic or the principle of this circuit. We need to have certain current here, so we apply a current source at the branch here. So this circuit is called now like mirror because it's going to make mirror for the current in this branch. So we got this current. What about the first MOSFET here? So let's make analysis for the first MOSFET to know what is the mode of operation for MOSFET number 1. So in order to do that, let's say now for MOSFET M1. So we have for MOSFET M1, we can say VGS1, the gate to source for VGS1 here. As you can see, VG is 0 for MOSFET 1. So let's say VGS1 equals, for sure, it's VG minus VS. But you have VG equals 0, as you can see here in this circuit. Gate is connected to ground. So this means this volt equals minus VS. So this is from the circuit. But how can we calculate VGS by means of current? Because we already got the current of that MOSFET because it's connected in series in the lower MOSFET. So from the circuit, let's continue this page. So from the circuit here, we can write now, guys, that the VGS for MOSFET 1 equals, from the current equation, again, so square root I drain for MOSFET 1, which is equal to I drain of MOSFET 2, divide Kn for MOSFET 1. This is plus V threshold. Okay, so this is the same current relation for saturation. So we assume saturation also here, and we will see if it is going to be in saturation or not. If not, so we can substitute in the other relation, the complex relation for non-saturation. So we can say now this equals 0.2 milliamp divide Kn for transistor 1 is 0.25 plus 0.4. So we'll end up with VGS equals 1.29 volt. Again, we said in the previous slide, as you can see here, VGS1 equals minus VS. So we can say now, since VG here is 0, we can say the point here, which is VS, this volt is VS1, we can say now VS1 equals minus VGS1. So let's say now, so we have VS1 equals minus VGS1. So this is equal minus 1.29 volt. So we got the node volt here. Now, in order to figure out the mode of operation for this transistor, we can calculate VDS1. And based on VDS1, we can compare it with VGS minus VT. If it is greater than VGS minus VT, so this means our transistor is working in saturation mode. Otherwise, it would be in non-saturation mode. So let's see now. Let's calculate VDS1. In order to do that, we can make now branch equation here using Kirchhoff. So we can say VDD. So this is here VDD, and we assume this is 2.5 volt here in this example. So we can say now, let's write the equation firstly. VDD equals RD times ID1, which is the current here. So this is here ID1, which we have calculated is 0.2 milliampere, plus VDS1 plus the volt at this node, which is VS1, so plus VS1. Now let's substitute in this relation, or let's get VDS1 in another side. So we can say now V drain to source 1 equals VDD minus RD times ID1 minus VS1. Now let's substitute in our relation. VDD equals 2.5 volt minus RD equals 8K times ID equals 0.2 milliampere minus VS1, which is minus 1.29. So this is minus like that. So in this case, the value of VDS1 would be 2.19 volt. Now, in order to figure out if this transistor is working in saturation or not, what is the value of VDS saturation. So you know that VDS1 saturation can be obtained as VGS1 minus V transistor N1. So what is VGS1? We already calculated VGS1, it's 1.29 volt. So 1.29 minus 0.4. So this one for sure now is working in saturation. So we can say now VDS1 is greater than VGS1 minus VTN1. So our transistor is working in saturation mode. So from this circuit, guys, we could find that we can control a current on another transistor by means of connecting this circuit to MOSFETs with common source, and the gate is connected to a drain of 1, and the reference current is coming from here. So this can be used for controlling any kind of current in any MOSFET. So this is called current or constant current of MOSFET. So this is the first objective of our class today. Nice. Now, we discussed many circuits in MOSFETs. We discussed the characteristics of MOSFETs. We figured out what the meaning of load line. We figured out the different modes of operation. Now, let's see together, guys, what are the most important applications of MOSFETs in our life. The first application for MOSFET used in our life is switch. So switch, you know, switch means we need to turn something on or off. This is the function of any switch. So switch is going to either connect or disconnect a certain circuit. So how can we do that? If you have a look to the characteristic of our MOSFET, we said we have 3 different modes of operation. The first mode of operation here, this can be obtained or the MOSFET would be off if we have V gate to source less than V threshold. So if VGS is less than V threshold, we are sure this transistor is going to be turned off, which means ID would be 0. So this is the first mode of operation, which is called cutoff mode. As you can see here, we have small value of current. However, this is just to figure out the graph, but this current would be ideally would be 0 current. Okay. And the other mode of operation we discussed also is the non-saturation mode. For the non-saturation mode, as you can see, increasing the value of VD with very small value increase of VD and increasing VGS, the current is going to increase. The ID is going to increase. So mainly we use VGS to control. So increasing VG is going to increase our current because the curve will be changed, and in this case, the current will be increased, as you can see here. So by controlling the switch or the transistor to be in this mode where VDS is less than VGS minus VT, this condition would operate our MOSFET in non-saturation region. And this is the second mode of operation that we need to operate the MOSFET as a switch. So switch means either connecting a load or disconnecting a load. So for instance, if we have a certain lighting load like that, and we need to turn on or off this load, we can connect this transistor in series or this MOSFET in series. And this is a shape of discrete MOSFET. So this is shape of one discrete MOSFET. We have a lot of shapes of MOSFETs. We will see some in our lab. This one is called discrete MOSFET, and this case style is called 220 case style. Okay, we have a lot of case styles and a lot of shapes of MOSFETs, and it's different according to the power. Okay, so this one is a small power, it's not very high power. You can find very high MOSFETs, by the way. It can reach to several kiloamperes. Okay, so MOSFETs can start from few milliamps, okay, and can work up to several kiloamps in high power application. So again, for this MOSFET, in order to control it to be switching on or off, we just can control the voltage here, V gate to source, this volt. So by controlling this volt by means of adding a circuit here to control this volt, we can turn off or turn on or off this switch. So if this switch is turned on, so this means the drain to source will flow a current here because we have a channel from drain source and we have now ID. So this means the load will be connected to ground. And from the other side, it's connected already to the supply volt VDD. So we will have a voltage drop across this load. And in this case, we can consider the switch is turned on. And if we have gate to source volt less than transistor threshold volt, so this means the switch is going to be off and ID would be 0. So this means it's equivalent to open circuit, and open circuit means there is no flow for this current here. And in this case, no ground will be connected to this load and this would be off. So these are the two modes of operations we use in MOSFET application as switch. So we never operate switch in saturation mode. So this mode is not allowed here to be used in case of switches. So switches all of time, guys, we are going to operate our MOSFETs in either cut-off mode. So first mode is called cut-off mode, and the condition of this mode is V gate to source is less than V threshold, and the second mode is the non-saturation mode. And again, you know, the condition of this non-saturation mode is V gate to source should be less than, V drain to source should be less than V drain to source saturation, which is equal to V gate source minus V threshold. Okay, so these are the two modes of operation that we use it in switch. What are the applications we may use it as switch? We can use it in very small power applications, and we can use it also for high power applications. One of the well-known applications we use in industry is controlling motors. So we can connect a switch MOSFET in series with a motor in order to control this motor. What the control technique, as you can see, it can now going to turn on and off. One of the well-known control techniques, guys, in power electronics called pulse width modulation, which means according to the pulse width of this switch, or the meaning of pulse width means I'm going to apply a certain gate pulses like that to this switch. So these pulses will have certain frequency. So this is the time of this cycle, and for sure frequency equals 1 over time, and it will have certain turn on time. So we have what's called the duty cycle. This duty cycle equals T on divide T, or we can say T on times frequency. The output volt of this circuit, which is going to be between these two terminals, okay, so this is the input and this is the output. So the output volt between these two terminals now will depend on the average value of the signal, which means now nothing but D times Vn. So we can say here V out equals D, which is the duty cycle here. This is called duty cycle. So V out equals D times value of input supply, which is Vn, and we can assume that the voltage drop across MOSFET is very small for high power applications. So this is the ideal relation for the circuit here. By the way, this circuit is called DC to DC converter or DC chopper. Why chopper? Because it's chopping the input supply volt. So if this supply volt is constant, the output supply volt will be similar to the pulses shape, okay? But the peak value of these pulses would be the value of the input volt here, okay? So by controlling now the duty cycle, which is this value, which is going to be controlled by means of the pulse width, which is T on, and the frequency. So by this way, we can control the output volt on a DC motor. And later on, you will learn in electrical machine course, if you control the output volt or the terminal voltage of a DC motor, you can control the motor speed. So this is one of the speed control techniques of DC motor. Okay, so this is one of the applications of a DC motor. Another well-known control technique used for motors in industry, guys, is called 4-quadrant DC chopper. So this circuit is called the 4-quadrant DC chopper, and it's very well-known, and it's used to control the motor in any direction, which means you can control the motor to rotate in clockwise or counterclockwise, and also the torque to be in positive or negative. So this means for any motor, guys, you will have what's called torque speed characteristic. So all of time for electrical machines, you have what's called output machine characteristic, and for motor, the output would be mechanical, which is going to be torque and speed. So for speed and torque, you can have different modes of operation, which means it can work in forward mode here. So this is called motor. It can work as reverse motor, and reverse motor means you are going to reverse the torque direction, okay? So the energy is going to be reversed, and in this case, it's going to be like operating in reverse power mode as generator, okay? Or you can convert both torque and speed to work as reverse motor, or you can reverse speed and the same torque direction. So this would be now like reverse generator. Let's say this is generator and this is reverse generator. So this is called 4-quadrant. How can we control the 4-quadrant operation? This can be controlled by means of controlling the 4 MOSFETs we have here. So we have certain techniques of control for this circuit, okay? And this circuit, as we said, it's called 4-quadrant DC chopper or class E DC chopper. Okay, you can find this circuit. By the way, it's very cheap now in industry, so you can get one chip. This chip including 4 transistors, including these diodes, and including even what's called driver circuit, because we need what's called drivers in such circuits in order to drive the MOSFET by the proper signal. Okay, so all of these can be included in one chip, and the module can be like $4 or $5 for small power applications. So if you have a motor, for instance, like around 40-watt motor, okay, you can with a small volt, like up to 24 volt, you can, or 12 volt, up to the motor you have, you can get a very cheap circuit composed of MOSFETs in order to control this motor. Later on in our lab, we can make a small project, but this is going to combine between electronics class and microcontroller class, because we need to provide some pulses from microcontroller to drive such circuit, okay? So we can make either this circuit or the simple circuit here in the previous slide to control the speed of a DC motor. Another application for the MOSFET is logic gates. So for logic gates, you know, logic gates are like OR gate, like NOR, like AND, like NAND, like NOT gate, and so on. So we'll have just here an example for a logic gate like NOR logic. So if we have two parallel transistors like that, and the input gate to these transistors is going to be our inputs to the logic gates. So now at the MOSFET, if we have 0 volt here, so this means we have VGS equals 0, which for sure would be now in cutoff mode. And if we have here also 0, so this is again cutoff mode. So cutoff mode and cutoff mode, the currents here would be 0. So in this case, there would be no connection between the point V out and the ground. And in this case, the current IR here would be 0 as well. And the voltage here would be the same as the voltage here. So if we apply 0, 0, we expect to have active high output. If we apply active high here and active low in the other side, so this means you would have now a voltage, and this is going to turn on this transistor, and for sure you will have some voltage drop here, VDS. However, the volt now, which is connected to V out, would be very less compared to the voltage V here. So we can consider that the voltage here is almost very small, and the signal at V out now would be active low, okay? Because most of the VDD volt will be consumed as voltage drop on RD. And in this case, the output would be active low. So once we apply active high signal, which is equal to VDD here in V1, so we are sure that the output would be active low. And since the transistors are connected in parallel, so if any one of them is turned on, so this would make the same result, which is going to be active low. So either this one or that one are on, either M1 or M2 are on. In this case, we would have output active low. And for sure, if we have both of them are turned on, so this means for sure we would have V out equals active low. So as you can see, guys, now we could get a result of active high if we have both zeros, active low if any of them is active high, any of the inputs is active high. So this is nothing but NOR gate, because you remember that OR gate means if any of the inputs is active high, the output would be active high. So for OR gate, if you remember, assume this is input 1, input 2, and this is output. So 0, 0 would give 0, 0, 1, 1, 0, or 1, 1 would give active high. So this is OR gate, and complement of OR gate is nothing but NOR gate. So as you can see, high, low, 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 high, high, high. So this is the complement of that one. By the way, if you would like to make complement for OR gate, you can add one more transistor, which is called inverter. And we discussed this in the previous class. We discussed one of the applications is inverter circuit, and we have it also in these materials, but this would be discussed in the next class. Okay, so this is enough for the class today, guys. Next class, we will have some examples on OR gate, okay, sorry, on the NOR gate, okay, and we will discuss the MOSFET as inverter and as amplifier. Thank you so much, and see you next class.